I welcome you to another lecture of quantum computing. In this lecture, I will describe entanglement. The plan of this lecture is as follows. Number one, I will define entanglement. Secondly, I will list Bell state and I will present the circuit that we can use to create Bell states. And finally, I will provide the proof of entanglement, that given some qubits, how can we check if these qubits are entangled or not. So let's start. Entanglement can be described using two different equivalent definitions. So according to definition number one, given a state of multiple entangled qubits, one cannot express individual qubits separately. So let's do an example to clear this definition. So in example, I have given an entangled qubit which is ket 00 plus ket 11 divided by square root of 2, and this is the entangled state of two different qubits. Because the state is entangled, so I cannot express each qubit separately. So I cannot find value of alpha, beta, delta, gamma such that the first qubit is alpha ket 0 plus beta ket 1, and the second qubit is gamma ket 0 plus delta ket 1. That means there is no value of alpha, beta, delta, gamma where the left hand side is equals to right hand side. So in this case we say these qubits are entangled. In contrast to that, we have separable qubits. So separable qubits. So that means that these qubits are not entangled and we can express them separately. Example is that I have a qubits ket 0 1 plus ket 0 0 divided by square root of 2, and I can express the state of these two qubits separately by ket 0 tensor product with ket 0 plus ket 1 divided by square root of 2. So in the second case, in the separable case, the value of alpha is 1, value of beta is 0, and value of gamma and delta is 1 over square root of 2. So now let's do the second definition of entanglement. Given a state of multiple entangled qubits, measuring any qubit individually reveals all other qubits. So now let's describe this definition using some examples. So the first example is of entanglement. I have ket 0 0 plus ket 1 1 divided by square root of 2, and these are two entangled qubits. Now before measurement, the probability that first qubit is 0 is half, and before measurement the probability that first qubit is 1 is also half. Similarly, before measurement the second probability the second qubit is 1 is half, and second qubit is 0 is also half. So before measurement both of those qubits are in superposition. Now we can measure first qubit. So we measure first qubit, and our result can be either 1 or 0 with equal probability. And if in case our result is 1, then we can close our eyes and we can tell that the second qubit is also 1. So if our result is 1, then the second qubit without measurement we can tell that it will also be 1. And if our first qubit is 0, then without measurement we can tell that the second qubit will also be 0. Similarly, we can measure second qubit first, and the result of the second qubit will also be either 1 or 0 with equal probability. And if the second qubit is 1, then the first qubit will also be 1. And we can tell the state of the first qubit without even measuring it or without even touching it. Even the first and second qubit might be physically thousands of miles apart. So if the second qubit is 0, then the state of the first qubit will also be 0. So that means this is the state of entangled qubit. In contrast to that, when we have separable qubits, then measuring maybe a first qubit will not reveal the state of the second qubit. So take this example where we have 0 1 plus 1 0 divided by square root of 2, and these are not entangled qubit. If I measure first qubit and the first qubit comes out to be equals to 0, then the second qubit will still be in the state of superposition. Without measuring second qubit, I cannot describe the state of second qubit. Second qubit can be either in a state of 0 with probability half, and second qubit will be in the state of 1 with probability half. So that means these are separable qubits, whereas these are entangled qubits. I hope that using these two definitions, the concept of entanglement will be clear to you. Now let's list Bell states and draw the circuit that create Bell states. Bell states. Also known as EPR states. We have 4 entangled qubits described as Bell state. First qubit is known as ket phi plus. It is also known as Bell state for 0 0 and equals to ket 0 0 plus ket 1 1 divided by square root of 2. The second Bell state is known as ket phi minus, and it is also known as Bell state for 1 0 and is equals to ket 0 0 minus ket 1 1 divided by square root of 2. Third Bell state is ket psi plus, also known as Bell state for 0 1, and this is equals to ket 0 1 plus ket 1 0 divided by square root of 2. The final Bell state is ket psi minus, also known as Bell state for 1 1, and is equals to ket 0 1 minus ket 1 0 divided by square root of 2. So let's see the quantum circuit that can create those Bell states. So the quantum circuit that creates the Bell state is extremely simple. So it takes two inputs. First input is ket I, second input is ket j, and it provides output an entangled state of Bell ij. So now you can see that why I have described these states as Bell 0 0, because to create this state you have to give I is equal to 0 and j is equal to 0, and the output of the circuit will be this state. If you provide I is equals to 1 and j is equals to 0, the output of circuit will be this state, and so on. So the circuit is that first you apply Hadamard on the first qubit, and then you use the result of the first qubit as a control bit to C NOT gate, and that's it. Now let's use this circuit to create a Bell state. So we can use this circuit to create any of these Bell states. Let's create this one. So to create this Bell state, I will give input, I will be 0 and j will be 1. So I give my input of 0 and 1. So maybe I describe different points where I can explain how the input is processing through the circuit. I say this state as ket psi 1, this state as ket psi 2, this state as ket psi 3. So my ket psi 1 will be equals to 0 1, because I is 0 and j is 1, and that is also can be written as ket 0 1. We know the tensor product can be written like this or can be written like this. So now what will be ket psi 2? So I will apply Hadamard gate on the first qubit while keeping the second qubit untouched. So my result will be 0 plus ket 1 divided by square root of 2 times second qubit of ket 1, and I can simplify this into ket 0 1 plus ket 1 1 divided by square root of 2. Now I have to apply C NOT gate. So in C NOT gate, if the first qubit is 0, then second qubit remains the same, but if the first qubit is 1, then the second qubit flips. So psi 3 will be equals to 0 1, because first qubit was 0, so second qubit will remain 1, plus 1 0. In this case first qubit was 1, so second qubit flipped from 0 to 1, for 1 to 0, and divided by square root of 2, and that's it. This must be equals to Bell state of 0 1, otherwise we have done some mistake. So let's check, and Bell state of 0 1 is same as psi 3. So at the end of the lecture, let's do a proof that given some qubits, how you can prove that those qubits are entangled or not. So I have given a qubit, say ket omega, which is equals to ket 0 1 minus ket 1 0 divided by square root of 2, and I have to find if ket omega is entangled or separable. So proof or solution. So we do the proof by contradiction. So it is once again proof by contradiction. So we assume that ket omega is not entangled. So we say that 0 1 minus ket 1 0 divided by square root of 2 can be written separately as alpha ket 0 plus beta ket 1 tensor product with gamma ket 0 plus delta ket 1. Now we simplify this expression. We will get on the left hand side ket 0 1 divided by square root of 2 minus ket 1 0 divided by square root of 2, whereas on the right hand side we will get alpha and gamma ket 0 0 plus alpha and delta ket 0 1 plus beta and gamma ket 1 0 plus beta and delta ket 1 1. And from this equation we can ascertain that alpha and gamma is 0. So alpha and gamma must be equals to 0 because there is no ket 0 0 on the left hand side. Whereas alpha and delta must be equals to 1 over square root of 2. So alpha and delta must be equals to 1 over square root of 2. Similarly, beta and gamma must be equals to minus 1 over square root of 2, whereas beta and delta must be equals to 0. So if beta and delta is equals to 0, then from this expression we can say that either beta is equals to 0 or gamma is equals to 0. If beta is equals to 0, then this expression will become 0. So therefore beta cannot be equals to 0, because if beta is equal to 0, then this expression will become 0. So beta cannot be equal to 0. If gamma is equal to 0, then this expression will become 0. So gamma cannot be equal to 0. That means both beta and gamma cannot be equal to 0. Therefore beta times gamma cannot be equal to 0. Hence this equation cannot exist. This is a contradiction. Therefore our original supposition that this qubit is not entangled is wrong. So left hand side cannot be equals to right hand side, thus proving that ket omega is entangled. And this finishes our proof. So entanglement has lots of applications. One application is quantum teleportation, and that is the subject of the next video. So stay tuned.